It's not just ATP and ADP. What we're looking at is these big, large, complex structures, which can be confusing to look at, which is why biologists ignore the structure and just write ATP. Okay? Fair enough. Okay? It's understandable. If you don't need to know the structure, you don't want to look at it because it can be confusing. So we abbreviate and use other symbols. Right? But if we compare those two structures to each other, ATP and ADP, the only thing that's really changing is these last atoms. Right? If we go through and compare back down, that's the only thing that's changed, is I've gotten rid of that phosphorus atom and those 3 oxygens. Right? Just the removal of 3 atoms provides enough energy for us to exist. Okay? If we do it a whole bunch of times. But, beside the point, that's our currency. Right? And that's kind of a neat process. So when we talk about what's happening on a cellular level in biology, a lot of those reactions or those processes are driven by the conversion of ATP to ADP. And as that happens, that single little molecule gets popped off. Okay? Not much larger than water, but ballpark. Okay? And that's enough to allow life to exist as we know it. Now, that's a pretty impressive feat. And that ultimately is coming back to chemistry. Okay? If we continue on our chemistry path and looking at our energy, we can talk about kinetic energy, temperature, and our physical states. Kinetic energy is the amount of motion. Okay? Kinesiology is all about the motion of the human body. How does it move, or how is it not supposed to move? Okay? That's kinetic energy. What is the energy associated with our particle as it moves? Okay? So if we take a look at those 3 boxes, okay, what do we have in those 3 boxes? What phases do you think might be represented?
Solid at the beginning.
Okay. We've got a solid probably in the first one. Then we have a gas in the second one, right? Oh no, okay. Why is the second one not a gas and the last one's a gas? Because it's blue. No. There's less space in the liquid. The gas one has more space between the individual particles. They even added some kind of animations-ish looking stuff to make it look like it's moving more. The gas particles are moving more. Okay, so there's more space between them. This goes back to what we talked about with compressibility in the first unit. If I try to compress a solid, well, those atoms can't compress. There's not a lot of white space, which means the most I could compress would be not even my finger width in between those atoms. But if we look at a liquid, there's a little bit more white space. So there's a little bit more compressibility, but not a lot. We move to a gas, there's now tons of white space. I can compress that significantly. Okay, so if we have an idea of what these phases look like down on that very tiny molecular level, we can come to better conclusions about what we're looking at. Right? The next part is the kinetic energy. Well, kinetic energy was the energy associated with movement. Which of those phases moves the most? Gas, which means its kinetic energy will be the highest. All right, how do we transition from a solid to a liquid?
Temperature.
What do we do with the temperature?
We raise it.
We increase it, meaning we're adding energy into the solid. What does that energy going into the solid do?
Makes the atoms more energetic.
Okay. Yes, they now have more energy. Keep elaborating on that. What do they do with that more energy? They move. So the kinetic energy is going up. We're adding thermal energy, and that gets converted into mechanical energy or motion. Right? What happens as we move from a liquid to a gas? What do we have to do to our temperature? We have to raise it again. That energy is going in to cause what to happen to each of those individual particles? Move more. So we're trying to convert or give more kinetic energy to each of those individual particles. That's what's causing the phase transition. And if we reverse it, what has to happen? We have to cool it down. By cooling it down, what are we doing?
Stopping or slowing the movement down.
How are we slowing the movement down? Yes.
By lowering the energy.
We're removing that kinetic energy. Okay? We're taking the kinetic energy away, which then means the particle can't move anymore because it doesn't have enough energy to move, and so eventually it stops moving, and that's where we transition into a solid.
Right, so you know how you can turn like gold into liquid?
Yes.
Could you turn it into a gas too? Is that like possible?
Could we turn any element into a gas? Yes. Probably not us, but yes. Okay. Why probably not us? It's got to be really, 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 really hot. Okay. Probably beyond the heat that we can do easily. Okay. There's probably some physicist out there that can be like, yeah, I can do that. Yeah, thanks. Okay. But we're probably looking more towards the sun generating enough energy to cause that to happen. There are other things that we can do to help transition into the gas phase without changing the temperature, but that's now looking at gas properties. We'll look at that later in this unit, but not right now. Okay? So, do all phases have kinetic energy? Do all phases move? Yes, technically they all move. Everything has a vibration, a motion associated with it. But solids, what would we say? There's hardly any movement within those. That movement is so subtle or negligible that we just assume they don't move.
Because if it did move, it would be an absolute zero.
No, don't go that far. Liquids. Do liquids move more than solids? Yes. But do they have free movement? No. Okay, so they have a restricted movement associated with them. They can still move, but they're restricted in the amount they can move. How about the gases?
They move freely.
Free movement all over the place. Right? So our kinetic energy will slowly scale upwards, or eventually scale upwards, to gas being the highest kinetic energy and solids being the lowest. Okay? So energy in our chemical changes. We can take water and add electrical energy to it. Okay, what happens? Well, that energy can get absorbed and it can convert water into hydrogen and oxygen gas. Okay? So if you've heard people talking about hydrogen fuel cells, this is something that we could do to produce hydrogen. Okay? And most hydrogen fuel cells are done this way. Okay? We pump electrical energy into water and we produce hydrogen gas. Okay? In a hydrogen fuel car, what do we then use that hydrogen gas for? Combustion. We react that with oxygen gas. They react and release a bunch of energy. That energy released is what we use to drive our cars. Okay? What's the byproduct? Water. And we say, well, we started with water. We ended or had a middle phase with hydrogen and oxygen. Well, oxygen I need to breathe, so that's a good thing. Hydrogen I'm using as my fuel. I reconsume the oxygen, so there's a net no change to the oxygen, and I produce water back. That looks incredibly like a clean process. That's got to be the wave of the future. Where did you get the electrical energy from? That's an interesting point. It's not actually specified where the electrical energy came from. Where does most of our electrical energy come from? Fossil fuels. So instead of putting gasoline into a car, you put gasoline into something else, cause that something else to make electrical energy, so that you can have the electrical energy turn into your fuel. You mean gasoline? Yes. Okay? So that you can then use that fuel to get energy back out. So instead of doing a direct energy conversion to get into our motion from gasoline to motion, we go gasoline to another fuel, lose energy, to then get motion, lose energy again. So our hydrogen fuel cars, at least within the energy system that we've created, are not going to be beneficial, because our gasoline cars are actually more efficient than this process is. Okay? How could we get the electrical energy where this now becomes a good process? Don't use fossil fuels. Okay? If we wanted to use solar energy to provide that electrical energy, then we've got something that we can work with, because we now aren't burning the fossil fuels at the same time. So when we go through and look at energy conversions and energy maps, we have to be considering where are each of those sources of energy coming from and where are they going. Okay? Every step of an energy process results in the loss. Okay? For instance, if I gave Alexis here 20 bucks, and I said now pass, or 20 $1 bills, and then I instructed you guys to pass it through. Everybody had to close their eyes, okay, and then pass the money along. What do you think Lucas is going to get in the back? He might be lucky and get $1. Okay? Because everybody had their eyes closed. There's probably somebody going to be like, I need 20 bucks. Here, have some paper. No one would know. And there goes the money. Each of those transfer processes results in a potential loss. So when we're dealing with electrical or any form of energy, anytime we convert that energy, we get a loss. Okay? This is one of the arguments why we want smaller government, because, well, the more people that touch that money, the smaller the money pot becomes. Okay? Which is a separate topic, so let's not stress about that. So, let's look at an interesting example that came up in your textbook. Okay? Is it better to fill your gas tank in the cool morning or the warm afternoon? So some people may have already heard of this. Okay? You're supposed to fill your car up when it's cold. Okay? Why do you want to fill up your car when it's cold? Okay, you get more fuel. What do you mean you get more fuel?
It's colder, so it's not expanding.
It's colder. So if we push this to the extreme, if it's colder, we're more like a liquid than we are a gas. Okay? And when we measure our gasoline out, are we measuring it by mass? No, we're measuring it by the volume. And if it's all gas, what happens? Look at all that white space that you're paying for that doesn't do anything. Okay? So we actually want to fill our gas cans when it's cold, because there's less white space. What we end up paying for is more of our gas molecule, the one that's actually giving us energy. Okay? It is not liquid to gas, though. What we're talking about is changes in temperature with just the liquid. How much money are you saving by filling it up when it's cold? It's like fractions of pennies per fill. Okay? Yes, you're saving money, don't get me wrong. Okay? But you are more likely to just walk around the gas station when you're filling up your car while it's hot out, finding money, spare change on the ground, to get more money that way than saving money by filling it up when it's cold. Okay? Just so you know. Okay? You do save money. So if you can do it, you might as well. Okay? So that is all our old stuff, which means we're now moving into chapters 8 and chapters 9. Okay? Or chapter 9. They're really kind of the same concept. Chapter 8 introduces a new conversion factor. Chapter 9 says we already have some conversion factors. Let's start putting all those things together. Okay? So what this is really going to do is take us back to the whole unit analysis method, or dimensional analysis, or the factor unit, whatever you want to call it. Step 1, write down what you want for your answer. Okay? What unit? Step 2, write down your given value. What if you're given 5 different values? Okay? How would you decide which one to use? Okay? So let's pick a quick example here, which I believe came from the test. See if I remember something about it. We have 63.6 miles per hour. We have 574 kilometers. I think I had another sig fig in there. And I want to know how many days it takes. Okay. So that's our question all put together. So if you really want the question itself, look at your exam, because it came off of your exam. Just to put this out there, 574 kilometers. Anybody know what 574 kilometers is referring to? At least one person does. You all took the exam right before spring break, right? I heard a lot of people just kind of randomly talking about things of what they were going to do during spring break. And a lot of people, for some reason, said they were going to Disneyland. Guess how far it is to Disneyland? 574 kilometers. Right. From, I think, the center of Phoenix, wherever that is. Okay. So, in any case, what do we want for our answer? Days. That is our unit that we want to start with, or end with, is days. Okay. We're now given two other values, 63.6 miles per hour and 574 kilometers. There's a mile there. Is days in the given information? No. So how could we possibly solve this? Okay, so one of the things that we need to be thinking about is, what do these units represent? What is days a measure of? It's a measure of time. So when I go back up to the given information, I want to be considering what those units are a measure of. What is miles a measure of? Distance. What is hours a measure of? What is kilometers a measure of? What do I want my answer to be? I want days, and where do I want it? Where do I want it? Okay. We've got numerator and denominator when it comes to fractions. If you don't like numerator denominator, that's okay, because I screw it up all the time too. Where is days located in a fraction? On top. Okay? Which means I need days to show up on top on the left-hand side, right? But I don't have days. Time. Time is my measurement. Where does the time unit show up? On the top. Which means, where does it need to show up on the left? On the top. So looking at my given information, I have one measurement of distance and one measurement of distance over time. So if I used my distance over time, and I dropped that down here exactly as is, because this is what a lot of people did, is said, well, I'm going to use my given information, and the 63.6 was given first, so I'm going to start with that. What is the problem with that? Where did you just place your time unit? On the bottom. Where do you want your time unit? On top. It's perfectly all right to start with this, but you have to recognize that you've placed it incorrectly. You want the time unit on top. How do we do that? We can do the inverse. The time unit is now in the correct location. It may not be the correct time unit, but it is the time unit. Okay? I now have a decent place to start. Is hours the same thing as days? No. Is miles in my answer? No. So I got to fix this. How do I fix it? Convert what? Hours, okay. I don't want hours in my answer, so hours needs to show up in the denominator in my conversion factor. What do I want to convert it to? Days. Do I know the conversion factor between hours and days? Yes. So I can immediately just put in some numbers. Those numbers would be 24 days was 1 hour, right? No, this is why you need to write it down and think about what you're entering. 1 day is 24 hours. What would happen to your units? Hours cancel and we would have days. Where would days be located? On top. Where did I want days? On top. Hallelujah, it's there. Okay. But I still have miles in the denominator, which means what do I need to do? I need to do another step here, where I'm going to place miles in the numerator, or on top. Why do I want to place it on top? So that it cancels with the unit on the bottom. Okay? Am I given miles? No. Because I'm not given miles, I'm going to have to do a conversion. What do I want to convert to? Why do I want to convert to kilometers? I am given kilometers. Okay? So now the question is, that's my ideal system. I want to go into kilometers. Do I know the conversion of miles to kilometers? How many of you memorized the conversion between miles and kilometers? You did not. So you don't know it. So what should you do? Check the first page. For exam 3, what could you do? check the first page and
My little note card.
check your note card. Because remember, that's the one thing we're going to change for exam 3. You are allowed to have a 3x5 note card. Yep, front and back. Okay, and you will be turning that in, by the way, the note card. Okay. So when we do that, what do we find? Oh, we are given the conversion factor. 1 mile is 1.61 kilometers. Why did I place the 1 in front of miles? Because when I look at the conversion factor, where does the 1 show up? Next to miles. Okay? I'm using the information that's given. I'm not trying to manipulate and flip numbers around. It's directly where that's found. What happens? Miles as a unit cancels. Awesome. I didn't want miles in my answer, but now what's the problem? I've got kilometers. Do I want kilometers? No. So I need to put kilometers in the next step in the numerator. Am I given just kilometers? Oh, yeah, I am. So what do? Write that number in there. What do I put in the denominator? 1 or nothing. Either is fine. If I put a number other than 1, I'm not writing the 574 that I was given. Okay? If I put a unit other than kilometers, I'm not using the information that was given. Does that make sense? What happens to your units? The kilometers cancel. What unit would I end with? Days. Do I have what I want? Yep. Now I can punch it into the calculator. Okay. I have no. Oh, it came out to roughly a quarter of a day. Okay. If we go through what most people went through and solved, I should have asked, is it okay if I just deleted all that?
Yeah.
Okay. Most people went through and said, well, we started with 63.6 miles per 1 hour. And they went through and did an awesome job doing this conversion. Miles, kilometers, is a 1.61. Miles. That L's bothering me. Okay. And I said, well, hours, days. Sorry, 24 hours is 1 day. And they said the kilometer deal, 574, is that what I said it was? 574 kilometers. And they said, okay, the kilometers canceled. The miles canceled. The hours canceled. Oh, cool, so it's perfect because I ended with days. And now when we look at it a little bit carefully, did you really end with days? What did you end with? 1 over days. That's not days. You solved for the inverse of your answer. Okay? You can do an extra step to get to your final answer, okay, but you have to do that extra step. Recognize where your unit, where you want it to be, and make darn sure that it shows up in the correct spot. Okay? So you've done an awesome job doing a conversion. Your unit work is perfect, but you didn't end up with the correct answer because you decided to just say, well, days can just magically jump up to the numerator. It can't do that. Okay? So don't force things to happen. You have to follow the work that is shown. This is why your work is good. Make sense? Your turn. We'd write down what we want for an answer, micrograms. What did we start with? Immediately, we're only given one thing, 325 milligrams. Okay. Milligrams is not the same thing as micrograms, so ideally, milligrams needs to cancel, and I would get micrograms in the numerator. Do you know that conversion? No. Okay, so you can't convert to microgram. What could you convert milligrams to? Grams. Okay, how do you convert milligrams to grams? What does milli mean? Ten to the, okay, This is fun. Okay? Sounds like two people decided to memorize this conversion the way I told you to memorize it. The rest of you did not. Right? So for those of you saying 1,000 and 10 to the third, where does that go? Right? This becomes the problem with this. You've memorized it, and I got some people telling me that 1,000 goes on top. 1,000 grams is 1 milligram? No, not at all. What you've memorized is half of what I told you to do. Okay? That your power of 10 should always go with the core unit, but then you have to memorize the power of 10, which you didn't. Milli is 10 to the negative 3. Okay? What you memorized is not necessarily wrong, you just memorized it wrong. 1,000 milligrams is 1 gram. I do not like that conversion factor because you're now putting the power of 10 with the complex unit. Okay? Which means, depending on what unit system you're working with, that power of 10 needs to change locations. Anytime you change locations, you've got a problem. Okay? That's why I don't want you to memorize it that way. That's why I told you not to memorize it that way. If you want to continue to use that way that I've erased, don't get it wrong. That's all I can tell you, because I'll just yell at you. Okay? So 10 to the minus 3 grams is 1 milligram. So that's great. We got rid of the milligrams, but now what's our problem? I have grams. What do I want for an answer? Micrograms. Okay, so again, I would have to set up this conversion. Micrograms, grams. Do I know that conversion? This becomes a questionable one. Some people seem to know it, some people don't. Okay, for those people that know it, why do you know it?
Because you just...
One option is you looked at the front of the test, and what does the front of the test tell you? Micro means 10 to the negative 6. Where does your power of 10 go? With the core unit. The core unit is grams. 10 to the negative 6, 1 microgram. Okay? So those of you that didn't have the test, you need that given information because you're not expected to memorize microgram. You're expected to use it when given. What happens? Your grams units cancel. What unit would you have now? Micrograms. What unit did you want? Micrograms. You're done. Okay? This conversion is relatively straightforward, or as straightforward as it's going to get for the rest of the semester. Okay? This is just powers of 10. So you can kind of cheat your way through this using tricks and traps and things like that from mathematics. If you've learned the King Henry nonsense, eats chocolate milk because milk is liquid, not a solid. You can tell I haven't memorized that. You can do that as long as you memorize that correctly. The issue again comes from you have to memorize it correctly. You're wasting your time memorizing information that is already given to you if you know the process. Okay? The biggest reason why I want you to memorize the process and not all that other stuff is for when we move into something along these lines. How many oxygen atoms are in 0.240 moles of O2? Well, what's a mole? A mole is 6.022 times 10 to the 23rd atoms. Is that a power of 10 conversion? Yes, there's a power of 10, but there's also this 6.022. That's not a clean conversion of just shifting decimal points. So if you've spent your time in that previous unit just shifting decimal points, you've shot yourself in the foot because you can't do this conversion factor now. Okay? That is why you need that process. Okay? So before we go looking at this conversion factor, why do we even need this? Okay? Well, we talked about chemical equations. Right? This chemical equation now tells me how I can make sodium hydrogen carbonate. Right? Why do I care? Why do I want sodium hydrogen carbonate? Has anybody ever baked before? Sodium hydrogen carbonate is baking soda. Do we use baking soda when we cook? Yeah, it adds air and fluffiness to whatever we cook with. If we didn't have baking soda, we'd be eating bricks, and that's not particularly fun. Okay, we want a little bit of fluffiness and texture in our food. That's coming from our sodium hydrogen carbonate. Well, how do I make that sodium hydrogen carbonate? Well, I make it by combining it with sodium carbonate, water, and CO2. Now that I have an equation, I can make some sodium hydrogen carbonate. When you go through to use baking soda, we could measure it out as a volume, which is technically inaccurate. It's better to measure it out via mass. Okay, so like really advanced bakers will tell you, you got to weigh your flour and all that stuff. I don't do that either, but you're supposed to do that, okay, and not do volume. So I want to mass that out. Well, if I want 5 grams of sodium hydrogen carbonate, how many grams of this stuff do I need? That's a good question. I don't know. Okay, let's just say I want 2 of these. Okay, let's ignore the mass. I just want 2 sodium hydrogen carbonates. How much CO2 do I need? 1. How did you know 1? It says so, not quite good enough. What is the number in front of carbon dioxide? 1. Is this equation a balanced equation? Yeah. How much water would I need to mix with that 1 CO2? 1. How much sodium carbonate do I need to mix with those? 1. So if I take 1 molecule of each of those things and mix them together, I get 2 molecules of sodium hydrogen carbonate. My chemical equation tells me that. Just like if I try to build a bicycle, I need to take 2 wheels in a frame to put it together to make a bicycle. This is the same process. I'm taking those component pieces and I put them together. Okay? Fun thing about bicycles versus chemistry. A bicycle, I'm pretty sure all of you could physically see, grab, hold, and at least move, right? Unless it's a really tiny bicycle or a really big one. Okay? Can you do that with these molecules? No. These are insanely tiny, so we can't grab just a single one and put it with another single one and put it with another single one. Okay? So what do we have to do instead? We take a whole bunch of one of those, a whole bunch of the other one, a whole bunch of the other one, and then we mix them all together to make a whole bunch of that one. Okay, but I want to quantify how much I produce here. Okay? So I want to take a whole bunch being 1,000 of each of those. Okay, what happens when I mix now 1,000 of those? Okay, cool. So we're now at a whole bunch, a large amount. That works. But if we can't grab a single one, will we be able to grab just 1,000? No, because when we grab, we'll probably grab 1,001. I wouldn't know that because I can't see that I have one extra one. So how would I go through and determine how much I have? I go into the lab and I measure it out. What am I going to measure out? The mass. Okay, well, that's not a big deal then. The mass just converts through. So if I give you 200 grams of bicycle tires, how many bikes can you make? If I gave you 200 tires, how many bikes could you make?
100.
Why are you so quick with that one, but not so quick with the 200 grams? The number of those things work to build the larger object. The mass does not. Our chemical equation doesn't tell us anything about mass. It tells us about the number of each of those pieces, not mass. The tricky part is that when we go into lab, we have to measure mass because we can't grab the number of each of those particles like we can with a bicycle. Right? So what mass would I have to do then to grab a reasonable amount? Okay, well, that then becomes a tricky system to deal with. To grab a reasonable amount of particles, or to get it to a mass that I can now measure, I have to grab on the order of 6.022 times 10 to the 23rd of those molecules. Okay? An idea of scale in that video, I think there were some stupid analyses or comparisons of like if you stacked donuts, 6.022 times 10 to the 23rd donuts, it goes some obscenely large distance. Okay? It's a really huge amount. Okay? But that huge amount of atoms will now get me up to a mass that I can easily measure. If I use anything less than that amount of atoms, well, now it gets me a mass that isn't as easy to measure. Okay? So the whole point of this conversion is to now take this number. I don't want to have to count out 6.022 times 10 to the 23rd atoms ever. Okay? I should have put that in the video. If you just started counting 1, 2, 3, 4, 5, 6, to count to that number, I think you would have to be reborn like 5 or 6 times. Okay? That's how long it would take to count. And even that 5 or 6 I think is wrong. I think it's like you have to be reborn longer than the lifespan of existence as we know it. Okay? So it's a really, really big number. I don't want to have to deal with that, so I'm going to get rid of that weird multiplier and that weird power of 10 and just say, well, that number now is 1. Okay? That makes life really easy. All that nasty and big number becomes 1. That's really nice. Okay? But it's 1 mole. It's attached to that unit. Okay? This is not an easy concept to wrap your head around. Some people just get it and move on and accept it. Other people fight it the whole time. Okay? So what we end up doing is saying, this is our conversion factor. We're trying to get things into this weird unit that you don't understand. Okay? But we want you to use it a whole bunch before you understand it. And so, well, that seems kind of backwards. Well, you only have now 6 weeks to learn this. Okay? And officially 4 weeks, because our exam is sooner than the end of the semester. Okay? Which means you need to start learning how to use it, and eventually the understanding comes along. Okay? That's the whole point of what's happening here. Okay? So how do we use it? Well, how many oxygen atoms are in 0.240 moles of O2? Well, what am I solving for? I want the oxygen atoms. What is the symbol for an oxygen atom? Define an atom for me. A singular unit, right? Okay, is O2 a singular unit?
No.
What is O2? It's a diatomic molecule. I asked for oxygen atoms. What's my symbol? I want O atoms. That's going to become important. What am I given to start with? .240 moles of O2. Okay? This is saying atoms. This is saying moles. Do I have a conversion factor that relates atoms and moles? Yeah, what is that conversion factor? Okay? So what I'm trying to do is focus on the unit and get that unit changed. Realize I will also have to focus on, sorry, I just want to rearrange this around. We'll also have to focus on the substance because the substance is going to become important as well. So, do I want moles? No. So that needs to show up in the denominator so that it cancels. What do I want? Atoms. So that should show up in the numerator. Okay? What am I trying to get rid of? Moles of O2. What am I trying to get? Atoms of O. When we go back up and look at this conversion factor, do you see the substance listed? All we're saying listed is mole and atoms. It's the measurement unit. It's not the substance. That's because when we do this conversion, we can't convert the substance. That conversion factor only allows me to convert the unit. As I've got written in my conversion factor, what am I trying to convert? The substance and the unit. That's two things, which means two conversion factors. Okay? Let's stick with just using the new one. So instead of going from moles of O2 into atoms of O, I'm going to go into atoms of O2. Does atoms of O2 make sense? Why not? What is an atom? A single unit. What is O2? That's a diatomic molecule. This isn't atoms of O2. This is it's molecules, which I abbreviate as MLCS because I don't want to write out molecules. Right? Does that mean my conversion factor is invalid? It means as it's written, it was poorly written. This 1 mole is not necessarily saying atoms. It's saying of anything. Okay. Thing being an operative word. Is a gram a thing? No, a gram is a measurement. Okay. I can look at a 1 gram brick and reference that brick as being a thing. But grams is a measurement. This is a thing. Are molecules things? Yeah, molecules are things. So I can say 1 mole of molecules is 6.022 times 10 to the 23rd molecule. Okay? Of molecules, or eggs, or donuts. Okay? Which means I can now use this conversion factor. What numbers do I need to place and where do I place them? Okay, since you were too slow, I'm going to give you the 1 mole. You have to give me the other one. Okay. What unit would we now have? Molecules of O2. Do I want molecules of O2? No. So I need to get rid of molecules of O2. So I need to place that in the denominator. What unit do I want? Atoms of O. Do I have that conversion factor? Yeah? Yeah? No, you were right with the yes. Where do we have that conversion factor? Just don't know how to get it. Okay. H2O has how many hydrogens? 2. How'd you know that? Says it in the formula. How many atoms of O are in a molecule of O2? 2. Meaning 2 atoms of O are in 1 molecule of O2. Did you know that conversion factor? Yeah, you may not have realized it, but you did. Your formula is a conversion factor. It provides you that context. You just have to interpret it. What happens now with your units? Molecules of O2 cancel, and you'd have atoms of O. So what do you need to do? Math. Punch out the calculator, beep, 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 boop, number. Kind of make sense? Okay. So it's a conversion factor to allow for measurable quantities. That's the whole point of Avogadro's number. Okay? That's why we use it. That's why it was created. Avogadro was the first one to note this issue. I want to go through and run a reaction, but I can't count those individual atoms. I need to use mass. How do I do that? Couldn't come up with it. Actually, he came up with it using gases, which gives us another conversion factor, which we'll talk about later. We later then went through and said, well, we can define a mole as the number of atoms. That allows me a conversion factor that simplifies everything. Because Avogadro was the one that acknowledged that issue first, when we determined that number, we named it after him. Okay.
Does he have any relation to the avocado?
No. The next thing that's kind of big that comes out of this, when we look at the periodic table, okay, for hydrogen, how many protons does hydrogen have? 1. How do you know that? It says so. Where does it say so? In the upper right-hand corner. Is there another number written in the box where hydrogen is? Yeah, what's that other number? It's 1.01. It's the atomic mass. Okay? What are the units on that atomic mass? AMU. Literally, atomic mass unit. Okay? So when you go into the balance room, you throw some stuff on there and it says AMUs. No, I didn't say that. When you step on the balance in the morning to figure out how much you weigh or how much weight you lost while sleeping, okay, it spits out AMUs. What, you don't do that? That's why I sleep in a giant trash bag. I don't sleep in a giant trash bag. It was like, wow, really? Don't do that. It's a bad idea. That's unhealthy. Don't do that. It doesn't spit out AMUs. Why does it not spit out AMUs? AMU is literally an arbitrary unit that we used to represent the number of protons and neutrons. Okay, so when we added those up, that gave us our atomic mass unit. When we look at our periodic table, the numbers that they provide there aren't whole numbers. That's not because we get fractions of protons and neutrons. It's because what's reported for the mass unit? The average mass for that element, because different elements have isotopes. Those isotopes have different neutrons, so we end up seeing an average mass reported up there. Okay? The beauty behind this number of 6.022 times 10 to the 23rd atoms is, guess what it does? It scales the atomic mass unit up to grams per mole. Which means if I want to use a reasonable amount of hydrogen, like a mole, and I want to measure that out, it turns out that that 1 mole of hydrogen weighs 1.01 grams. AMU ends up being grams per mole, okay, or can be related to it. That is the sheer awesomeness of that number. It's not just scaling it up arbitrarily, because we could just say it goes up by 10,000. But it's 6.022 times 10 to the 23rd. That's not just a factor of 10. That's some weird floaty number. Why did we pick that weird floaty number? Because that takes all of our AMUs and puts it into a single unit that allows us to now directly interpret off the periodic table the mass relationship per mole of that substance. Okay? That is insanely useful. Okay? So if I take 12.01 grams of carbon, how many moles did I grab a hold of? 1. Because the mass for carbon is 12.01. If I want 2 moles, let's pick something easy, 2 moles of helium, what is the mass I need to measure out? 4 is the mass for 1 mole. I asked for 2 moles. So it's 8. Okay? You're doing a conversion factor in your head. That process I want you to start writing down, okay, and working through that. You're doing it and you're doing it well. You just have to remember where that information is found. If you look at exam 2, there was that question with moles and grams, with hydrogen and water and all that fun stuff, and you're like, I have no idea. Okay? Look back at every place where there's an equality, erase that. That's going to be on your next exam. You're responsible for knowing where those conversion factors are found. Where are they found? Periodic table, chemical formula, chemical equation. Okay? Everything stacks. So, your turn. What is the molar mass for copper 2 nitrite? So let's break some of this down before we get entirely into it. Whoops, I knew I advanced a slide. Molar mass. What do you think molar is in reference to? Moles. How do we measure mass? Grams. So when I'm asking for the molar mass, I'm asking for the mass in grams for, yes, 1 mole. So what this question is asking for is the grams per mole. And I know I just wrote that, and I'm now just erasing it. Grams per mole. Grams per mole of what? That's my measurement. What's my substance? Copper 2 nitrate. No one wants to write out that copper parentheses 2 nitrate stuff, so we do the Cu parentheses NO2 2. Per mole of what? Grams of copper 2 nitrate per mole of what? Per mole of copper 2 nitrite. Okay. How do we figure out that conversion? Am I given anything? I need to figure out the mass of copper in a mole. Yeah, where would I find that? In the periodic table. So if I look at the mass of copper, what is the mass of copper? 63. 63.55 grams per mole of just the copper. Okay. So that's cool. I know that amount of copper is in copper nitrite because it says there's 1 copper in it. That's what my formula tells me. What else is in my formula? Nitrogen, right? We could go through and do nitrite. What's the problem with doing nitrite? Point to nitrite on the periodic table. It's not there. So we'll have to break that down into the individual elements. I need nitrogen. So what is the mass of nitrogen?
14.01.
14.01 grams per mole. How many nitrogens are in copper 2 nitrite? There's 2 because of that parentheses, right? So it's not just 14.01, it's 14.01 times 2. What's the mass of oxygen? 16, is it just 16? Yeah, 0.00 grams per mole. How many oxygens are there? Okay. There are actually 4. We have the 2 as a subscript outside the parentheses, multiplying in, but then we also have the 2 inside multiplying. So we get 4 oxygens. What happens if I add all those numbers up?
How did you get 4 oxygens again?
I'll rewrite it in just a second. What happens when we add all those up? I get the grams of copper nitrite per mole of copper nitrite. That's it. So I now have a conversion factor that relates copper 2 nitrite's mass to its moles, found using the periodic table. It's just a question of adding those terms. Back to the oxygen. There's 2 oxygens in every nitrite. There's 2 nitrites. Okay, kind of makes sense? This will become relevant here in a second. Does somebody go through and do the math? 155? 13?
57.
Should we be worried about sig figs? I still not do it right.
0.57. 0.57.
Should we be worried about sig figs? We would really hope not. At this point, more than likely what we're going to be testing on is the concept of moles, not testing on the concept of sig figs. Which means, when you look at your multiple choice answers, you won't see a difference in sig fig numbers. You'll just see the answer written and varying ways to add those numbers up. Because you could have just added 63 plus 14 plus 16. Okay? That would have been a wrong answer because that didn't account for each of the elements or the total of each of those elements. Okay? So you probably won't have to worry about sig figs. Okay? Is this number particularly useful? Well, I don't know. What's the next question? What is the mass in grams of 0.532 moles of copper 2 nitrite? So again, let's set it up. What do we want for an answer? The mass. And in particular, the mass in grams. So that's my measurement unit. What's my substance? The copper nitrite. What was I given? I was given 0.532 moles of copper 2 nitrite. Are moles and grams the same thing? Nope. So I need to do a conversion factor where the moles, copper nitrite, 2 nitrite, need to become the grams of copper nitrite. Does anybody see that conversion factor in the question? No, it's not there. If you check the front of the exam, you aren't going to see it on the front of the exam either. Where are you going to see it? On the periodic table. You have to go through and determine the grams per mole. What was that? Yeah. So for those of you even considering that, remember that's a really big joke because all I have to do is change this compound to something else, right? And for thinking of all the compounds, just pull out the nomenclature sheet and determine the molar mass for every single one of those. Fit that on a note card for me, please. Okay? Use the periodic table. That's the whole point. Okay? Yeah. Okay? So, did we determine what that conversion factor was? Yeah, in fact, I literally just asked that question for this very reason. What did we decide that conversion factor was? 155.57 grams was 1 mole. Now I have my conversion factor, and the moles of copper nitrite cancel, and what would I have? Grams of copper nitrite, copper 2 nitrite. I keep dropping that too. And we'd have our answer. We now just have to do the math, punch it into the calculator. Okay, if you really don't like your calculator, you can even really punch it in. Just be very specific. Okay? Kind of, sort of? How bad? Where are we? That's horrible, let's blow up chemistry, or, yeah, that's not too bad. Nobody? Okay. What is the mass in grams of 2.55 times 10 to the 23rd atoms of lead? Your turn. Well, actually, let's pause on that. Do you want the setup? Yeah, let's do the setup. What do we want for an answer? Grams of lead. Since we don't like writing out lead, we would write PB. Because we memorize that that's the symbol for lead. Okay? It stacks. Okay, what were we given? 2.55 times 10 to the 23rd, I lost it, atoms of lead. Okay, that's your setup. Okay, we can jump to the potential first step. Okay, and just so you know, this is a two-step one, but if we try to do this in one go, atoms of lead to grams of lead. Do we have a conversion that gives us grams to atoms? No. The conversion we just talked about on the periodic table was grams to moles. Okay, so we don't have this conversion factor. We need to decide what we want to convert to. Do we want to deal with the grams of lead and try and convert that into something, or do we want to take the atoms of lead and convert that into something? I would make the argument it is easier to convert the atoms of lead into something than it is to convert the grams of lead into something. Okay? So for those of you saying, okay, that's not too bad, please continue the setup. No, that is the setup. You're done. Okay? Atoms of lead, we need to convert into something. We can't convert it into the grams of lead outright, so we're going to try and convert the atoms of lead into something else. That something else should help us eventually get to the grams of lead. Okay? We're really kind of in a box. If you really have no clue, then you are dead in the water there. There's nothing you can do. Okay? Ideally, what you would recognize is that we just talked about what we can convert atoms to. What could we convert atoms to? Moles. And if we're now in the moles of lead, what could we do? Well, moles of lead is not grams of lead. Okay, so I would need moles of lead in the denominator, and ideally I would get grams of lead in the numerator, or on top. Okay. Is that a conversion factor I'm required to know? Or can find? Where can I find it? That's on the periodic table. How about the moles to atoms? You're required to know that one, sort of. You got me doing avocado now. Avogadro's number. Okay. You should really memorize Avogadro's number. That said, if you take a look at the front of your exam, I believe it's actually on there. Okay? But yeah, you don't want to be flipping back and forth if you can prevent it. That's the whole point of memorization, is to minimize that extra step. So Avogadro's number is what? 6.022 times 10 to the 23rd. So I write 6.022 times 10 to the 23rd. No, what did the 6.022 times 10 to the 23rd show up in front of in our conversion factor? Our atoms. Okay? So it's not just a blind writing down of the number, it's writing the number with the unit that it's supposed to go with. Okay? And what number do we write in front of moles? 1. Periodic table told us our grams per mole for our lead, and that number would be 207.2. So 207.2. It's remembering what it's tied to. It's tied to grams. It's 207.2 grams per mole of lead. Okay? You have to remember where those numbers are tied, what unit they're tied to. You can't just place them randomly. Okay? For those of you thinking about this and saying, okay, it's not too bad, I would never make a random mistake. Literally, each of these is a 50-50. Okay? You could go through and do the homework and get the answer right every single time, but happen to luckily guess where you should be placing that number. Okay? With this conversion, you now have 2 steps here. If you at least knew those knew that you needed those conversions, you could still guess and be guessing right a quarter of the time. Okay? 25% is not a passing grade in this class. So make sure you tie the number with the unit appropriately. That's how you decide where the numbers go. It's the unit, not the number. So every time we write these out, notice, what am I writing out first? The unit, because the unit's going to tell me where to place the number. Okay, makes sense? What is the mass in grams of a single molecule of sulfur dioxide? It was pointed out, class is almost over. That's why I only gave you 30 seconds. Grams of a single molecule of sulfur dioxide, so grams of SO2. Okay. What am I starting with? I don't see any numbers. You're starting with 1. 1 what? molecule, which is not a mole, this is our MLCS, of sulfur dioxide. I want to convert that 1 molecule into grams. Okay. If we go through and look at this, here's my molecules of SO2. Ideally, I'd go into grams of SO2. Do I have that conversion factor? Nope. So what can I convert the molecules to? Atoms doesn't work. SO2 is by definition a molecule. I can't go into atoms of it because atoms wouldn't be useful, because what am I solving for? A molecule. Okay? So I don't want to convert it into atoms, I want to convert it into moles of SO2. Okay? Why moles? We'll address that in a second, but at this point we're really just trying to fire away and come up with something to convert to. What is that conversion factor, or where is that found? This is Avogadro's number. 6.022 times 10 to the 23rd molecules is 1 mole. So cool, I've gotten rid of molecules, and I'm now in moles. I want to get rid of moles of SO2. What do I want to get instead of moles? Grams of SO2. Where do I find that information? Oh, yeah, I did give it to you. Officially, you can find it on the periodic table, or if Mike's really nice, he gave it to you. Okay. I didn't mean to give it to you. I apologize. I meant to make it more difficult. 64.07 grams is 1 mole. We can now go through and punch this into the calculator, and what kind of number are we going to get? Really big or really small? Really, really, really small, because we're dividing by 10 to the 23rd. So small that we would never be able to measure this. And that's where we want to end.